Congruent figures. Let's talk about congruent figures. In geometry, congruent figures are figures that have the exact same size and shape. It's not enough that they have the same size. It's not enough that they have the same shape. They must have the same size and the same shape. When two figures are congruent, one of the ways that we can discern that they are congruent is that we can take one of the figures and slide it right over the top of the other one, and it matches up perfectly. For instance, if we had two post-it notes, and we ask the question, the post-it notes congruent? Do they have the exact same size and shape? Well, one of the ways we can tell is if we can take the post-it notes and stick one on top of the other. If they match up perfectly, well, then we can tell they have the same size and shape. What are some of the other things that we can do to try and discern whether these figures are congruent? Well, as I said, we have this idea of sliding. Can I slide one over the top of the other? So if I have two figures, can I slide one over the top of the other? If I can and they match up perfectly, then they're congruent. The other thing is, can I flip one? So perhaps I have two figures like this, and I'm asking the question, well, if I flip it, if I flip it like this, will it go over the top of the other one? That's a question we might have. And then the third question is, well, what if I have to turn it? Can I turn it to get it to go on top of the other one? At the end of the day, the real question is this. Is there any way I can rearrange one of the figures so that it will fit exactly on top of the other figure? Now, when we do geometry, and we're looking at a piece of paper, and we have numbers and values on the paper, generally speaking, we don't just whip out our scissors and cut the paper up and slide it on top and see if it fits. And even if it did, sometimes it'd be hard to look through the two. So there must be another way, a geometric concept that we use to try and figure out if figures are, in fact, congruent. When we talk about figures, really, right now we're focusing just on polygons. All polygons, okay? So, when we talk about congruent polygons, what are we talking about? Well, we're talking about polygons that have congruent corresponding parts. Each of their corresponding parts has to be congruent. What do we mean by corresponding parts? Well, we're talking about sides and angles. So, for instance, if I were talking about my two hands and asking whether they were congruent, I need to look at the thumb and all four of the fingers and the palm, the fingernail, everything. I need to look at every part. And in any polygon, when we talk about all the parts, we're just talking about the sides and the angles. That's what makes up a particular polygon. So, for instance, if I were to look at this particular pentagon and ask the question, well, I guess it's not closed. Let's just close it up. I missed. There we go. Alright, you imagine that that's closed. Just work with me here. Okay, if I wanted to construct a polygon, a pentagon, that was exactly like that one, I would need all of the same sides and angles. Now, probably you're looking at that and saying, Mr. Picard, that's really not that great. You didn't do that great of a job. One of the ways that I can show you in geometry that it does have the same sides and angles is simply to mark each of the corresponding sides and angles. You can see that if we were to mark each of those and the sides, those are just the angles. The angles by themselves are not going to carry the day. I need to know also that all the sides are congruent. So maybe we'll mark one of those and those, two of those over there, two there, 1, 2, 3 there, 1, 2, 3 there, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. You get the idea. If I can show you somehow, symbolically, that each of the corresponding parts from the triangle on the left is congruent to those other parts on the right, that is the corresponding parts in the, I think I said triangle, in the pentagon on the right, then we'll know for sure that the two pentagons are in fact congruent. Notice that we need to match vertices when we talk about the corresponding parts. Sometimes this can be a little bit tricky. Just because the two triangles that I happen to be looking at, the two polygons I happen to be looking at, are sitting on the page a certain way, does not mean that their corresponding parts are up and ready for analysis. For instance, if I gave you two shapes like this, you'd want to compare my thumbs to each other, my index fingers to each other, and so forth. If I do like this, well, you wouldn't start comparing my pinky to my thumb. Right? You have to make sure you match up the vertices. And sometimes that happens just by a process of elimination. So, for instance, if I had two triangles like this, and I told you that this vertex here, that one there, is congruent to this one here, and this one is congruent to this one down here. We ask the question, well, how are we going to match these up? How do we align these in order to decide whether they're congruent? Well, you can see that this vertex corresponds to this one over here. And this vertex corresponds to this one here. It has nothing to do with their relative position on the page. It has everything to do with whether they are congruent parts. So I'm trying to match up congruent parts. When you name congruent polygons, you always list the corresponding vertices in the same order. Okay, always list them in the same order. Let's look at a quick example of that. Here again we have an example of two triangles, and again we ask the question, well, can we make a congruent statement about these triangles? Remember, triangles are always named by reference to their vertices. We start at one vertex and we go clockwise or counterclockwise. So in this case, the triangle on the left might be called triangle ABC, and maybe it'd be called triangle CBA. Doesn't make a difference. Triangle on the right might be called triangle XYZ, or it could be called triangle ZXY. It makes no difference. Those names are both fine. But when I make a congruent statement, it's very important that I name corresponding parts of the triangles in the same order. So, for instance, if I want to compare triangle CAB to the triangle on the right, I have to say that triangle CAB is congruent to triangle YXZ. I have to name the corresponding parts in the same order. It would not be correct, and again, this is sort of visual. We're just sort of looking at this, and we can sort of see that the corresponding parts, that vertex vertices rather, A and X correspond, and B to Z. So I cannot say that triangle ABC corresponds to XYZ, because those are in different order. It has to be ABC corresponds to XZY. We need to be careful about that as we name the triangles and write out congruent statements. Alright, question is, how do we find congruent triangles? How do we look at two triangles and know for sure that they are in fact congruent? The answer to the question, at least at this point right now, is, well, we need 6 pieces of information. Okay, 6 pieces of information between the two triangles. We need to know that each of the 3 corresponding angles is congruent, and we need to know that each of the 3 corresponding sides is congruent. Okay, with less information than that right now, we're really not in a position to say. As we move forward, we'll begin to ask the question, what's the minimal amount of information we need to determine that 2 triangles are congruent? I know I can say, yeah, okay, if I have 3 sides and 3 angles, then that's enough. But can I do with less than that? The answer, of course, is yes, I can do with less than that. And the first theorem we'll look at is called the third angle theorem. It's pretty straightforward. It says if 2 angles of a triangle are congruent to 2 angles of another triangle, then the third angles are congruent. So if I have 2 triangles, and 2 of the angles are congruent, and let's suppose we know the following information. We know that this triangle is congruent to this, that angle is congruent to that angle over there, and this angle is congruent to this one down here. Okay, notice there's no given information about the third angle. There's nothing that's being stated about this angle here or this angle up here. We don't know anything, at least nothing has been given to us. But the third angle theorem says, listen, if these angles, this angle here and this angle are congruent, and these 2 angles are congruent, then the third angle must also be congruent. This is nothing more than a straightforward application of the triangle angle sum theorem. Already, we've gone from 6 pieces of information that are needed to determine that triangles are congruent to 5. When I say 5, what am I talking about? I'm saying now we only need 2 angles. 3 sides and 2 angles. That's enough information, because we know if we've got 3 sides and 2 angles, that actually gives us the third angle, and that's all 6 pieces of information. So the name of the game here is to see how much less information we can use in order to arrive at a determination of congruence. Let's just look at a couple examples and see if we can't make sense out of this. Just some basic questions on whether or not triangles are congruent. Alright, let's look at a triangle over here, and another one over here. Alright, we've got 2 triangles. Suppose we know the following information. Alright, suppose we had this problem on the screen here, and you can see we have triangle ABC and triangle XYZ, although those might not be corresponding parts I've named there. As we begin to analyze it, we're looking for parts that could potentially correspond, and we're trying to ask the question, hey, do we have any congruent triangles here? So we have, again, A, B, C, and so as I name these in that order, I'm going to try to name this triangle in the same order. You'll notice that I come across side AB. This is called side AB right here. Oops. And you'll see that it has 2 tick marks on that side. So when I name this triangle over here, I need to come across side XZ. Okay? So it's AB corresponds to XZ. And then from ABC, I go across this side with 3 tick marks. So that's my second side is ZY over here. So it's XZY. And then you'll see, of course, that from C to A, which is the last side, I have a single mark. And from Y to X, I also have a single mark. So my inquiry at this point is, hey, I'd like to answer this question. Is triangle ABC congruent to triangle XZY? That's the question. Now, I know that the sides are congruent, so I've got 3 sides. And the question is, do I have 2 angles? Well, as you can see, I only know 1 angle on each triangle, so I don't yet have enough information to determine congruent. I need more information in order to answer that question. So suppose I gave you the following information as well. In addition to these 60-degree measures, you also knew that you had these 2 50-degree measures. And now we ask the question again, is triangle ABC congruent to triangle XZY? Well, now I've got 2 angles, and by the third angle theorem, I know that angle A must be congruent to angle X. Therefore, I've got 3 angles and 3 sides, and I can be absolutely certain that these triangles are congruent. That's basically how we work through it. In summary, we've looked at just a couple basic concepts. One is this question of how do we determine whether 2 polygons are congruent, and the answer to that question is if they have all the same congruent corresponding angles and congruent corresponding sides, then we find that they're congruent. In triangles, that means that we need 3 congruent sides and 3 congruent angles. And so far, we've learned this one theorem, which is the third angle theorem, that says listen, if you have 2 angles, that actually tells you that the third angles must also be congruent. By the way, that doesn't tell you whether you've lined everything up properly. You still have to line up all of the corresponding angles appropriately. That's it for Congruent Figures for now. If you have any questions, shoot me an email.